In this video lesson, we're going to discuss significant figures, why they're important, and how to determine how many significant numbers a number might have. In the following video, we'll look at how to calculate with significant figures. So let's take a look at the blue object on the screen. Suppose I give you this blue object and I ask you to measure the length of the blue object, and I give you 3 meter sticks in order to do so. The following meter sticks that are below the blue object are all exactly 1 meter long, but you'll notice that they are calibrated differently. Okay. So let's suppose I ask you to measure the length of the blue object using the first meter stick only. Don't look at the second and third meter stick to do this practice. Alright, the only thing we know about the first meter stick is the fact that the end of it is 1 meter and the beginning of it is 0 meters. That's all you know. So if you were to start imagining little marks with your mind, you would see that the blue object is approximately 0.2 or perhaps 0.3 meters long. However, if you were to say that the blue object is 0.21, for example, or maybe 0.37, you'd be going a bit too far because you're actually guessing farther than you can. This is where we start to get into digits of uncertainty. You see, the only marks you know for sure, or in other words are certain about, is the 0 meter mark at the beginning and the 1 meter mark that's at the end. Therefore, the rule is you can only guess or be uncertain about one digit. So, for example, looking at the length of the blue object, you could say that it's 0.2 meters, but that's it. Going any further would actually be guessing 2 digits of uncertainty. Alright, let's take a look at the length of the blue object using the second meter stick. The second meter stick has the 0 and the 1, just like the first one, but you can also see that the meter stick is divided into 10 equal parts. So now, looking at the length of the blue object using the second meter stick, we can see for certain that the blue object is in between the 0.2 mark and the 0.3 mark. So when we write 0.2, we're actually certain that it is 0.2 something. Now, if we look at what the length of the blue object would be between 0.2 and 0.3, this is where we start guessing again. Looking at that length, you might guess that it's 0.27 or 0.28. But once again, this is where we get into our area of uncertainty. Therefore, that's as far as we can go with the length that we record. And so perhaps we'll say the length of the blue object using the second meter stick is 0.27 meters. So to review up until now, using the first meter stick, our digit of uncertainty was in the tenths place, and our digit of uncertainty using the second meter stick was in the hundredths place. Alright, let's take a look at the third meter stick. Not only do we see that the 0 and the 1 mark is there, as well as it's divided into tenths like the second meter stick was, now each individual area between there is also divided into tenths. If I were to real quickly zoom in, you could see that that is what we see there in between the tenths mark. So, we can see that using the third meter stick in order to record the measurement, we are definitely certain that it's 0.2. We are definitely certain that it's 0.27, but now once again we start to have to guess. This is where it would get tricky because those spaces are really small. Nevertheless, you could see that it is marked to the tenths place and therefore we were able to guess one more digit. Perhaps we think it's a 1, and so we could record the measurement as 0.271 meters long with our digit of uncertainty being the ones place, the number 1, or in other words the thousandths place. Alright, let's talk about this for a moment. Some students might say, well, it's not really accurate in order to guess that. And you'd be right in saying that your error would increase as you start to get smaller and smaller markings. However, nonetheless, we do need to mark off that thousandths place in order to show that the third meter stick is as accurate as the first. For example, perhaps when you were measuring the blue object using the third meter stick, you said, I think it actually is exactly 0.27. I don't think that 1 should be there. Alright, nevertheless, if you think it's exactly 0.27, you still need to record the 0. Otherwise, if you just leave it as 0.27 meters, you're saying that the third meter stick is the same accuracy as the second meter stick. And we can see visually that that's not true. So we have to record that 0 in order to show that it is more accurate than the second meter stick. This is where we start getting into significant figures. The first meter stick recorded the length to 1 significant figure. The second was to 2 significant figures, and the third meter stick was 3 significant figures. This is why significant figures are important in science because it's showing us the degree of accuracy that our measurements are. Now that we know why significant figures are important, let's go ahead and take a look at the rule. When we look at the rules for significant figures, it comes down to 4. The first rule is very simple. It states that all non-zero numbers, or in other words, numbers that aren't zero, are significant. So for example, if I gave you the number 1.932, notice all of those numbers are not zero, and so they would all be considered significant. And so in that example, there are 4 significant figures, the 1, the 9, the 3, and the 2. It gets tricky when zeros come into play, so let's take a look at the second rule. All zeros that are in between non-zero numbers are always significant. I like to call this the bookends rule, because these zeros are sandwiched in between non-zero numbers, much like bookends would sandwich books. So if anytime there are zeros in between 2 non-zero numbers, they are also counted as significant. Therefore, in our examples, the first number would have 4 significant figures, the 1, 2 zeros, and then the 1, as well as the second number would also have 4 significant figures. The zeros count because they're in the middle. The third rule says that beginning zeros, in other words, all zeros to the left of the first non-zero number, are never significant. So in other words, if there are zeros at the beginning of a number, we do not count them as significant. So in our example, we see those zeros that are at the very beginning are not significant. And so our significant figures start with the 2, the 3, and then the 4, totaling 3 significant figures. Now, you may say, well, why are they there if they're not significant? They're there because they are placeholders. We need to make sure that they're there, so we show that the number actually starts in the 10,000ths place. The final rule is the one that I think can be the most tricky. We call them ending zeros, or in other words, zeros that are to the right of the last non-zero number are significant only if there is a decimal in the number. I just like to think of this as ending zeros. So if there are zeros at the end of a number, they will be significant if there is a decimal place. Now let's not be confused. Sometimes students say, well, are they to the left of the decimal or to the right of the decimal? It doesn't matter. As long as there's a decimal in the number, then ending zeros count. Take a look at the 3 examples. You have, on all 3 examples, zeros that are at the end of a number. So all we have to do is figure out, is there a decimal somewhere in the number? And if there is, those zeros will count. In the first number, 400, there are zeros at the end, but there's no decimal, and therefore they don't count as significant. So there would only be 1 significant figure. In the second number, 5.00, there are zeros at the end, and there is a decimal in the number. Therefore, those zeros are significant, and total, there are 3 significant figures. Finally, there's a 400 point. Those zeros are at the end, and since there is a decimal in the number, those zeros do count, and there's 3 significant figures. Now, sometimes students stop and they say, wait, you're telling me that 400 grams would be 1 significant figure, but 400 point grams would be 3. So simply adding a decimal makes the number more significant. Why should this be? The reason why is because as a scientist, when I see that there's a decimal at the number, that's telling me that the number could have been potentially 401, 402, 399, and so on. But that decimal is telling me it is actually exactly on the dot at 400. 400 without a decimal tells me that the instrument used to measure that mass was a little bit more inaccurate, and therefore we have to show that in the number. Some quick practice. Pause the video and then you can resume to see the answers. In the first number, there are 4 significant figures. Second number, there are 5. Third number, there are 3. In the fourth number, there are 5. In the fifth number, there is 1 significant figure. 303 would be 3 significant figures. 1,000,000 would be 7 significant figures. And the last number would have 4 significant figures. Just a quick note before we end, exact numbers, which are numbers that we use when we're just counting something, are not going to be determining our number of significant figures when we do a calculation. So for example, if I ask you what's in a dozen, it would be 12, whether that's 12 donuts, 12 eggs, 12 flowers, etc. See, the number 12 is an exact number. Same thing with metric system conversions. In 1 meter, there's exactly 1,000 millimeters. These are numbers that just come from counting, not from measuring. And so when we get into some calculating, which we'll do in the next video, these numbers will not be basing our Sig Figs when we're calculating.